that tonight's homework does not cover questions 6, 7, 8, or 9. Nope, 6, 7, or 8. I did have that up a minute ago. I don't know what happened to it. Let's see. There it is. So 6, 7, and 8 you'll leave out tonight. And then, like I said, we're going to do most of 7-2 today, most of 7-3 on Friday. And then Monday, we're going to do the rest, whatever we don't cover for 7-2 and whatever we don't cover for 7-3 on Monday. So Monday's sort of like a trig potpourri. And it will be nice because what I'll do on Monday is I'll put in a bunch of sort of like review type exercises in the lesson activities as well, so that you can start doing a little bit of a review of the stuff we've covered. Okay, so that's tonight's homework. I think I also have the book in here, right here. So here's our textbook for 7-2, and I want to point out to you what we're not going to cover in section 2, because there's a large part of section 7-2 that we won't cover. Every time you see this product to sum and sum to product identities, if there are like 1 or 2 of you in the class that actually read the book, so this is like 423 all the way through the rest of the book, almost through the rest. We're not covering product to sum and sum to product differences. So I've gone through and taken those homework questions out of 7-2. But if you're reading, you don't need to read that. Okay. So let's quickly go through and put these values in here. So I'm just going to go right around the room, pass if you're not comfortable, starting with Rich. Rad 3/2. I like that language. Rad 3/2. I'm going to use that. Okay, go on right around. Go ahead. Okay. Okay. If any disagreement, let me know. Benny? 3/2? Okay. Anna? And Irene? Okay. So these we're going to be using over and over again, along with, of course, their radian values in today's lesson. Today's lesson and on Friday and then again on Monday, we're going to be looking at lots of new identities. Can you shut that, Jenna, please? So if we were asked to find the cosine of the sum of 2 angles, we see that these 2 angles equal 90 degrees. And we know that the cosine of 90 degrees is 0. We just found that out up there, right? Well, we also knew that. So the question is, if you take the 90 degrees and you divide it up to 30 degrees and 60 degrees, is it as simple to say that the cosine of 30 degrees plus 60 degrees is the cosine of 30 degrees plus the cosine of 60? In other words, does it act like the distributive property? So we know that this answer is 0, since these two are the same. And then over here we say that the cosine of 30 is 1/2, and the cosine of 60 is 1/2. And is that true? Cosine of 30 is 1/2 and cosine of 60 is 1/2? Is that right? No? Why not? Which one? Cosine. Square root of 3/2. That does not equal 0. Oh, shucks. Life couldn't be that simple, right? So then you come down here, and I'm giving you another one to try. Cosine of 90 we know is 0. And we also know that the cosine of 90 equals the cosine of 30 degrees plus 60 degrees. And now we're asking, does it equal this kind of funky expression over here? So let's take a look at that. It's the cosine of your first angle times the cosine of your second angle. Notice your sign changes, right? This was a sum in here, and now it's become a minus up here. So the sign changes, and now it's sine's turn to play with each one. Sine of 30 degrees times sine of 60 degrees. So with this cosine here, we're dealing with the like things first, cosine of each angle, and then we're subtracting the sine of each angle. Let's see if we can get a 0 out of here. Cosine of 30 degrees, if we go up to what we were just doing, is square root of 3 over 2. Cosine of 60 degrees is 1/2 minus sine of 30 degrees is 1/2. Sine of 60 degrees is square root of 3 over 2, and that certainly equals 0. So there's our first identity. If we have the cosine of two angles, let's call this angle A and this angle B. So it's the cosine of the sum of two angles. If we have the cosine of the sum of two angles, it's the cosine of each angle times, it's the product of the cosines of each angle. Then we change our sign from plus to minus. That's the big change with cosine. And then it's sine's turn with each one. Okay. So that's what we get. This is going to be the cosine sum identity, the sum of two angles. Now we play the same game with sine. Did we get that sine of 30 plus 60 was equal to sine of 90? No, it's not that easy. And I thought I fixed this typo. I even took, you might notice you have two staples in here. I tore off the first page and thought I fixed it. So let's see what this next one is. Is the sine of 30 degrees plus 60 degrees equal to the sine of 30 degrees times the cosine of 60 degrees plus the cosine of 30 degrees times the sine of 60 degrees. So let's see. Sine of 90 degrees we know is 1. Sine of 30 degrees is square root of 3 over 2. Cosine of 60 degrees is is the sine of 30 degrees square root of 3 over 2? It's 1/2. Don't let me tell you lies. Pay attention. 1/2 times the square root of 3 over 2 plus what? What's 1/2? Cosine of 60. Oh, okay. You're not letting me get away with anything, are you? 1/2 times 1/2. All right, now plus cosine of 30 degrees is square root of 3 over 2, and sine of 60 degrees, square root of 3 over 2. So what's that equal? 1/2 times 1/2 is 1/4. Square root of 3 times square root of 3 is 3/4. 1/4 and 3/4 is 4/4, which is 1. Woohoo! So there's going to be our second, and we're going to derive some of these. So if we have the sine of two angles, the sum sine of two angles, then that is, now sine is sort of like an equal opportunity trig function. It's sine of A times cosine of B. We want everybody to have a chance here. And then cosine's going to get its chance with A, cosine of A, and then sine of B. And they're all written down there for you. You don't have to write them down. Okay, I do want to point out that this is pretty much, you notice that it's sine of A, cosine of B. Then most books write it this way because they want to keep the order of these angles the same. So sines and cosine have had its chance, and again, equal opportunity. Then they go, okay, now it's cosine's turn with A, and sine's turn with B. But some people also think of it this way, and it doesn't matter. It's just the order, and we know multiplication doesn't matter. Some people like to say, okay, they like to keep this order the same, and that's okay. They do sine B times cosine A, and that's all right. It doesn't matter whether you keep the angles in the same order or whether you keep this product in the same order. They just switch. All right, so here are the 4 angle identities. And after you see one of these proofs, which you're about to see, you really can derive all of the other three. I may leave that for an exercise at some point. So what we're going to do is we're going to take a look at proving this. Okay, we're going to look at the difference identity for cosine, the difference between two angles. Now, this is where I want to say to you, it's going to be impossible for you to watch what I'm doing and write what I'm doing, because there's a lot of algebra in what the proof we're about to do. So what I would prefer you to do is, this proof is in your textbook. The difference is your textbook uses one circle with the 4 points we're going to look at. They use a little different diagram, and they justify it a little differently than the route I'm taking, in terms of why the distance between the 2 points we're looking at will be the same. But the actual proof is the same. You could listen to the video later or copy it out of your textbook. I think what's best is right now is pay attention, and if you have a question about something I'm doing, to ask the question, because it's more important that you stop me if I do something you don't quite understand. I just want to say to you that the algebra that this proof uses has to do with how you square a binomial. And we know this is not x squared plus y squared and x squared minus negative y squared, or x squared minus y squared. It's x squared times double the product of those two things, and then you square your last term. So this is the idea that we're going to use throughout this proof. The only difference now is that cosine x and y may be like cosine of x and cosine of y, okay? Or sine of x and sine of y if we were doing another identity. So that's the only difference, is that these things are just going to, your visual field's going to just look a little crazier. But it's this idea that we're using. All right, so let's take a look at this proof, because it's important now we start doing a few proofs along the way, because you'll be seeing proofs when you get to calculus. So we're trying to prove the formula for the difference of two angles, the cosine of the difference of two angles. And we just said that the cosine of the difference of two angles is the cosine of A times the cosine of B. The sign changes to plus, and then it's signs turn, sine of A times sine of B. That's what we just saw on the first page. So we have to somehow get a proof so that when we're done, this side and this side will be equal. So here we go. So we know on the unit circle that if I take 2 points, that the coordinates of this point here, let's label this point P, I'll try to be consistent with your book, and this point Q. And that we know that the angle from the terminal side here, your x-axis over to P, that angle we're going to call A, angle A. So the coordinates of point P would be cosine of A, sine of A. Similarly, we're going to take point Q, and we're going to say that that's B radians. The angle there is B radians. So this will be cosine B, sine B for our coordinates. All right. So what we want to do is we now want to find the distance from P to Q. What's the distance of the line segment from P to Q? So to do that, the distance of the line segment from, A to B. Nope, how about P to Q, Linda? P to Q. We have to use our distance formula. So that's the square root of the difference in our x coordinates squared plus the difference in our y coordinates squared. That's our distance formula. So we're going to have cosine of A take away cosine of B squared plus sine of A take away sine of B, whole thing squared. Okay. Now we have to square that out. This is just like x take away y square, t take away u square, okay? It's what I just showed you a minute ago. So let's do that. So I get the first term squared, cosine squared A. You won't have enough time to write all this down. I'm guaranteeing it. Double the product, then cosine squared B. That's this first thing squared out plus sine squared A minus 2 sine A sine B plus sine squared B. Okay, there we go. Now we want to simplify this. Our Pythagorean identity is going to come up over and over again in every part of this trig chapter. Cosine square A and sine square A gives me 1. And guess what? I have another cosine squared A and another sine squared B. So those two things here and here and here and here become 2. Woohoo! Right? 2. So we get 2 minus 2 cosine of A, cosine of B, minus 2 sine A times sine B. All right, we're done with that. All right. Now what we're going to do is we're going to take this circle and I'm going to rotate it B degrees. I'm going to take this whole circle and just turn it B degrees clockwise. So this side is going to go B degrees clockwise. So it's going to come right down here and rest along your x-axis. All right? So that's why we can't see it over here. So this side right here is now right here. Okay? And then this side right here has just been rotated B degrees. So it's going to be up here. So all I did was rotate it. The angle, this new angle, will be A take away B. When I move it, it's A take away B. So now let's find 2 more points on here. Let's call them C and D. And as you can see, or maybe not see just yet, since I've just rotated these 2 sides, the distance from, well, I won't say that yet. Since I've just rotated this, I now can find the distance between these 2 points because the coordinates of C will be the cosine of the angle A minus B, comma, sine of the angle A minus B. What are the coordinates for point D right here? It's not a hard question. 1, 0, thank you. So now we have to find the distance from C to D. Whoa! All right. Distance of the line segment from C to D. So that's going to be the cosine of A minus B, take away 1 and square it. Cosine of angle A minus B, take away 1, square that. Plus the sine of A minus B, take away 0. Oh, thank goodness, we get a little bit of a break there with the 0 and square that. So what's this going to equal? Cosine square of A minus B. Ooh, it's almost what we want. We want a cosine of the difference, right? Minus 2 cosine of A minus B plus 1 plus 2 sine square of A minus B. Okay, can I do anything there in terms of simplifying? Oh yeah, I got another cosine square and sine square. So that gives me 1, and then I've got this one to join it. So I get square root of 2 minus 2 cosine of A minus B. All right, so I found the distances of those 2 line segments. Now what must be true about our 2 distances? They're the same, right? These sides haven't changed. The angle has, but they're exactly the same length. Okay. So we say this, the distance from P to Q, is equal to the distance from C to D. So all I have to do now is copy these 2 distances, and I'm not going to rewrite that. I'm going to use my little camera and cheat a little bit. So I'm going to take this thing right here. Thank you. Send it to my clipboard. Come on. Put it down here. Paste. Oh, not that big. All right. Oh, okay. So that's P to Q, and that's going to equal, I got to make it a little smaller. That's going to equal the distance from C to D, which I have right above here, the square root of 2 minus 2 cosine A minus B. Okay. Some proofs can take a long time. All right, so how am I going to solve this equation? What do I got to get rid of? Square root. So I square both sides, and that undoes the square root. So I get 2 minus 2 cosine of A times cosine of B minus 2 sine A times sine B equals 2 minus 2 cosine A minus B. Almost there. So what do I do here? I can subtract 2 from both sides, and that gets rid of that 2. Yes? Everybody? All right. So what do I have? I now have this 2 cosine of A times cosine of B minus 2 sine. It's really starting to look like that identity now, equals minus 2 cosine of the difference between A and B. This is what I want to solve for right here. The cosine of the difference between two angles. I got to divide both sides by -2. Once I do that, I am home free. So this gives me cosine of A times cosine of B plus sine of A times sine of B equals the cosine of A minus B. Thus, it is proven. QED. Okay. So there's your first identity and the proof. Now, it's only a little bit of a stretch to think about how would you prove the cosine of A plus B. And if you change the cosine of A plus B to this, A take away a negative B, then you can get you'll have the same type of proof. Jackson? I don't understand why. Well, you can either rotate, you want to rotate it because we have to establish two distances in order to prove this. So that's one way to do it. The other way to do it would be to pick 2 points on the same circle so that instead of thinking about rotating it, you pick 2 other points so that their angle is A minus B. And you'll get and then you can do, if you remember geometry, side angle side proves 2 congruent triangles, then you can show that the 2 distances are equal. But a lot of people it's been years since they've had geometry, so I thought that staying away from a side angle side proof and just going to the idea of rotating it the same number of degrees it does the same trick. Okay, it's just 2 different approaches. Other questions? Okay, so as you can see, and this is going to be true, you will hear my words throughout calculus, especially when you get to Calc 2. It's all the algebra. It's not the calculus, it's the algebra. So again, if you're still stuck with squaring binomials and calling them things like x squared plus y squared, you've got to make yourself like huge reminders, okay? Because a lot of what's happening now, especially when we prove identities today and tomorrow and Friday and Monday, it's just algebra. It's arithmetic a lot of times. Hazel? Sure. I think you should all work through this yourself. Work through this again. It's in your textbook. It's in the video. I'm not saying I'll put it on the test, but I would feel comfortable putting it on the test. Okay. All right, so how can we use these sum and difference identities? They can be used for a lot of things. You can rewrite angles and find exact values of angles that are not on our unit circle, where the reference angle is not on our unit circle. We can rewrite expressions. We can simplify expressions we couldn't have simplified before. And we can prove new identities. And what I left out of here is we are also able to solve some equations that we haven't solved before. So let's find some exact values. So cosine of 15 degrees. The first thing I have to remember is if I'm going to use my calculator to check this, I have to make sure I'm in the right mode. that I'm in degrees. So I got to go down here and check there. Okay. So you might say, why the heck do I need to see this? Because I can throw cosine of 15 degrees in the calculator. That's true. Let's do it just to see what we get. Cosine of 15. But this, so 0.96592, blah, blah, blah. All right. So we'll just put that down there for now. But the idea of being able to use these cosine and sine difference in sum identities will come in handy throughout the rest of your section here when we're proving identities and also rewriting expressions. So what we want to do is we want to write 15 degrees either as the sum of two angles we know or the difference of two friendly angles. So what do you think you might do here to get 15 degrees? 45 degrees minus 30 degrees. That sounds good. I know cosine of 45 and 30, and I know sine of 45 and sine of 30, so that's a great place to start. So cosine of 15 degrees can be rewritten as the cosine of the difference between these two angles. 45 degrees, take away 30 degrees. Okay. And now I use my cosine identity. The first thing I do is I remember cosine changes. Oops. Changes the sign. So I'm just going to put a plus over here because I know that definitely happens. And I know cosine likes to keep things, like cosine is like, I was trying to think of ways to help you remember this. And cosine has even symmetry. It reflects around the y-axis. It kind of likes to keep things kind of together and looking nice. So I don't know, you can make up your own story. That's how I remember it. So cosine sticks to itself for a while here. It just is cosine of each angle. There we go. And now it's sine's turn, sine of each angle. Everything's sort of like in order here. Okay, so then you take each piece one at a time. Cosine of 45 degrees, square root of 2 over 2. Cosine of 30 degrees is square root of 3 over 2. Sine of 45, square root of 2 over 2. Sine of 30 is half. So that they both have the same denominator, which is 4. We get square root of 6 over 4 plus square root of 2 over 4. So this is the exact answer. Square root of 6 plus the square root of 2 all over 4. Your calculator can only give you an approximation. So we are now capable of finding exact values. All right, well, if we can do it in degrees, we can do it in radians. So think of this. This is 1/12 pi, or 1 pi over 12. So I want to think twelfths. I want to either add two numbers to get 1 pi over 12 or subtract two numbers that are radians to get 1 pi over 12. So what comes to mind? Anybody think? Keep it in twelfths and then we'll reduce it. How might I subtract two things and get 1 pi over 12? Anybody got an idea? What did you try? Yeah. Pi over what? Yeah. That's fine. If we change it to twelfths, pi over 4 is the same as 3 pi twelfths. And this is what? 2 pi twelfths. Okay. So that's where I start. I say 3 pi over 12, take away 2 pi over 12. Gives me 1 pi over 12. But unless you're used to using the unit circle with the twelfths idea, then I would call this pi over 4, take away pi over 6, because that's how I'm used to working my unit circle. So this becomes the sine of pi over 4, take away pi over 6. So now it's pi's turn. Sine's turn. So sine is an equal opportunity employer. So we get sine of pi over 4, and then it's cosine's turn. The sine stays exactly the same with sine. And now it's cosine's turn to take the first angle on. and then sine takes on your second angle. Or you could just say sine of the second minus cosine of the first, however it makes sense to you. And you do need to tell yourself a little story along the way to have these make sense to you or remember them. But really the way you remember them is you're going to use them over and over again. And as you use your little notes for the first few, see if you can remove your notes and just, have this internalized for yourself. Okay, so what do we have here? Square root of 2 over 2, cosine of pi over 6, square root of 3 over 2, minus square root of 2 over 2, minus a half, yeah? Everybody agree? Yes, no? Don't ask me. I don't know. So once you get these formulas written out, they're really just kind of plugging in the information. Okay. I guess I don't even have this on here. All right. Any questions on the first thing we can do with these new identities? Anything at all? You'll find out. You're not going to ask me when are we ever going to use math again, are we? After all the stuff you've been doing in engineering? You'll see. A lot of stuff is, you can't always show where you're going to use things until you get there, right? All right. So the next big thing is proving identities. And on your first test, and I did this for you on your first test. I asked you to prove an identity on your first test. And you came down to something like this on your left side. To check out, there was some steps that brought you down there. And the right side looked like this from the very beginning. That was the right side at the very beginning. I don't remember what this side was. But anyway, after you did a few steps, you got there. And then, and I wrote this comment on everybody's quiz test who did this. A lot of you added cosine squared to both sides. You can't do that when you're trying to prove or verify an identity. You have to keep these sides totally separate, like separation, of state and church in our government. You got to keep them separate. You can never cross the equal sign. Never cross the equal sign in bold. You can cheat and look from one side to the other to see if you're getting to where you want to go. You can manipulate each side, but you can never cross like you're solving an equation. Okay, so those of you who added cosine squared to both sides, you can't do that. What you have to do is say, oh, that equals sine squared theta. And now you've proved that identity, whatever it was at the beginning. So if you look back on test 1, you'll see if I've written something there or not. A lot of you added the cosine squared theta to each side. Okay. So maybe I wasn't like as clear about that when we did that. I thought I was, but now I've written it in bold letters, okay? Let me tell you something about identities. If you're one of these students who like to play a little bit with math, you could be doing identities from now until the end of the summer and not do all of them. I mean, there's just so many identities out there that could be verified or established or proved that you could just be doing this forever. There are ways after you have some practice with identities that you'll see little sort of strategies. You'll get to say, oh, this is one where, yeah, I've got a fraction and I've got to make common denominators top and bottom, or this is where I use the formula for the sum of two angles. You'll get there. So this last thing is really important. Don't be discouraged if your first attempt fails. Try something else. You don't become good at doing identities unless you do a lot of them. And most of you are not going to have time in your life to do as many as teachers have done, right? So we have some example, but there's no like template. I can't give you a template and say, every time you see an identity, you do this and you do that and you do this. It's not a cookbook. There are strategies I can I can tell you about to try to use that might help you see your way through the forest, okay? So here are some of them. Use known identities. We know this identity. We could replace sine square x with 1 minus cosine square x, which we just did. Okay, that's from the Pythagorean identity. Sine square x plus cosine square x equals 1. Any variation of that, that's used quite a bit. And of course, all the identities we're about to learn. Rewrite everything if you can in terms of sine and cosine. That's one strategy. You might do it to both sides, or you might do it to one side and see where it leads you. Work backwards or in both directions at the same time. Look at where you ended up, where you want to end up, and work backwards. Find common denominator for fractions. That's a biggie. Factor whenever possible, and then these last two. So we're going to prove this identity right here. Okay, we're going to prove this identity. So I'm going to take a picture of it and put it on a separate page. Oh, I didn't take a picture of that. There we go. Send to clipboard, give me a new page here. Paste. Okay, here we go. So, do I know where to go when I look at an identity? No. When I first see an identity, I don't know whether I should start on the left side or the right side. Sometimes they say start with the side that's more complicated. That's what you hear some teachers say. Okay? I don't know which side to start with here. You might say, well, geez, we just looked at these identities. Shouldn't we write those out? Maybe. Should we write these out in terms of sine and cosine? Probably, since one side has sine and one side has tangent, we're going to probably have to do that. But here's the key. Put a huge, as big as you have, a big marker that you have, a huge red line right down the middle like that. And never shall the two sides cross, ever. You got to start with whatever you have at home or available to you now. Just put that red line right down there. You've got to keep one side separate from the other. That's a big, big important idea. All right. Does anybody want to start somewhere and we'll see where we end up? I mean, I know where to start, but I'm not going to say anything. Let's try it together as a group. What do you want to do, Jackson? Put the tangent side in terms of sine and cosine. Okay, so this very first term here, tangent of A is going to be sine of A divided by cosine of A. Oh, God, I got fractions. I hate fractions, right? Hopefully you don't hate fractions. Plus, we got a tangent of B sitting right beside it. So that's going to be sine of B. Ooh, good. I'm starting to see lots of sines here, but I also see cosine, Juck. All right, over cosine of B. Try to, when you do these, take a nice breath and just see it as an exploration. Don't worry about grades and stuff like that right away. Just see it as, oh, these are going to be like, I know, I don't want to say fun, because I know it's not fun for a lot of you. Then we do the same thing to the bottom. It's like when my physical trainer says, oh, these core exercises are going to be fun, Linda, I know she's going to kill me. So sine of A over cosine of A. Then I have a subtraction. And then, am I running out of colors? No, I still have blue. Sine of B over cosine of B. Okay. Is that fine with everybody so far? Anything that you have any questions on? Well, that doesn't look anything, well, really, if I wrote over on the other side what the sine of A plus B looks like, it's sine of A cosine of B plus cosine of A sine of B. It's not quite looking like that yet. What can I do with this thing? What might be a next step? Think arithmetic, someone other than Jackson. Yeah, Jenna? I can take the reciprocal when it's a single fraction in the denominator. Right now, I don't have single fractions. Multiply what by cosine, and what type of cosine? Okay. Yeah, you multiply top and bottom by the same thing. But which cosine? I got two cosines there. Okay, but you're on the right track. Maybe someone can pick up your idea and take a little further. You're shut off, like at a bar. You're shut off. I know you're too young to go to a bar, but you're shut off. Other people have to take a shot. No, because then you're not keeping it the same, right? You got to do the same top and bottom, or right, numerator and denominator. So you can't, right? You mean over here? Because you're dividing by two different things. You could divide by the same thing. Benny? One fraction. How would we put these two fractions together? What would we have to do? And this is where you were going. What would you have to do to put these two fractions together? Find a what? Common denominator. 2 prime. You think of those as 2 prime numbers like 2 and 3. What would be your LCD? 2 times 3. What's the common denominator for this? Not AB, because you got more than an A and a B here. Cosine A times cosine B. All right? So this is arithmetic moving up to a little bit of algebra. This is the hard stuff. It's not the fact that we're working in trigonometry. And this is what I keep telling you about. This is where it's going to keep happening. So you want to make this into a single fraction that just has cosine A times cosine B in the denominator. You want to squish them together. So to make this fraction equal to that fraction, you multiply top and bottom by the same factor, because that's just a fancy form of 1 right there. So you've got sine A times cosine B plus sine B, and now what are we multiplying this fraction by? Your other denominator, which is cosine A over cosine A. You have the right to multiply anything by a form of 1. So we've now squished it together so we have a single fraction. Yeah, I haven't finished. Times, I was just looking for my, I was talking and not finishing, cosine A. There we go. All right. So you squish them together. There's your denominator. It's just a product like 2 times 3. Let's do the same thing for the bottom one. You're going to have exactly the same denominator in the bottom. The denominator in the bottom is cosine A times cosine B. So you multiply top and bottom of this one by cosine B. Top and bottom by cosine B. That's your fancy form of 1. And top and bottom of this one by cosine A. You got to see these a couple times, and then you'll get them. I wouldn't expect you to know like the first few times you're going through this. So what do you have here? You have sine A times cosine B. Take away sine B times cosine A. So now you have a single fraction on the top divided by a single fraction on the bottom. Now Jenna's idea, I think Jenna said multiply by the reciprocal, right? Dividing by anything is the same as multiplying by the reciprocal. What's going to happen when I flip this and multiply? They have the same denominator. So those are going to become 1. I'm not going to do that for you. I think you can. So what do we have left? Our numerator is sine A cosine B plus sine B times cosine A all over sine A times cosine B, take away sine B times cosine A. The top is the sine of A plus B, and the bottom is the sine of A minus B. Therefore, you've established the identity. So you will have a few of those for homework. You may have to try a couple of different strategies, but you'll get there. It's really more about perseverance and staying with it, because you have every technique you need, either from arithmetic or algebra, to prove these identities. All right, I think we've almost gotten through all of the things we can do. I think there's one other thing I have to do. Oh yeah, two more, third and fourth. Third, we can use these identities to solve equations. Oh no! What am I going to do to solve this equation? Again, a few helpful hints. Do you recognize this as the potential of one of your identities? Cosine sticking together and sine sticking together. You're used to having it this way, the cosine first and the sine, but you can change the order. This is the cosine. Look, if you just change the order, it might help you. So addition is commutative, so you can just change the order of it. And you say, oh yeah, this is one of my cosine identities. Which one? Oh, there's a plus in the middle, so it must be a difference of two angles. And my angles are x, take away 2x. So I simplify my left side to this. Now, x take away 2x is negative x. My negative angle identities, or I think of my symmetries, cosine is an even function. It has symmetry about your y-axis. So the cosine of the opposite of x is exactly the same as the cosine of x. So I can replace this with the cosine of x equals the square root of 3 over 2. And now I have a baby equation to solve. Okay, baby equation. So I take the cosine inverse of both sides, cosine inverse of the cosine of x undoes the cosine of x, and I get x, and on the right side I get the cosine inverse of the square root of 3 over 2. So x is going to be, where is cosine positive? It's positive in the first quadrant, so it's pi over 6 plus 2k pi, where k is an integer. It's also positive in the fourth quadrant, so if I go down clockwise, pi over 6 minus pi over 6, that leads me to 11 pi over 6 plus 2k pi, where k is an integer. You can do this on your own. Create that identity, just using your sign for the sum of two angles. You can start your lesson activity there, because I have to stop talking. Okay. Those were